got the quiz on chapter 2 today, the homework quiz on chapter 2. So we'll start out with any questions on chapter 2. Is that 46? Okay.
I'm confused because I think that I saw the answer. I saw the answer, but I feel like I don't understand it. Like the inertia to pull a piece of towel off of the roll.
Right. So, a couple different approaches to it. One, objects tend to want to keep doing whatever they're doing. So, if you have the paper towel roll sitting there, it wants to stay at rest. So, anything that you apply to it, it still resists the wanting to move, since it's starting at rest. So, if you do, so now you're going to be applying a force. If you do a slow pull, you're applying a low force. A fast pull, you're applying a louder force. And everything has a breaking point. So, you'll hit that breaking point more easily, and it's more apt to sort of give way to, so that the main part of it does not move.
Okay, I see.
That, okay. I think one of the Hewitt videos talks about that. I seem to recall seeing him do the pulling a paper towel off a roll before. Right now, doing questions from chapter 2 textbook problems. Yes, ma'am.
Page number 5.
Number 5?
Max six.
Oh, this textbook for right now.
Okay. Oh, okay, I'm sorry.
Yeah, so basically the way I'm picturing it is we'll do the textbook questions now, then we'll do the quiz,
Okay.
and then after that, I'll take the master set question.
Okay, for number 35.
35, okay?
Okay, so I drew the four vectors, and the difference between A and C wasn't that big. Maybe because of the way I drew it. Are we supposed to just eyeball it?
So, you're just ranking the net force on the stumps. You're not ranking which set of forces is more likely to rip the stump out. So, A, they're perpendicular to each other. That seems more visible. B, they are, think like that, and then C. All these lines are supposed to be the same length. So let's actually try to do something like that. So that. Roughly. So from just a straight up adding vectors, and this relates to the question that you had, Jasmira. If I add them together to get the total force, well, I've got one that's going this way of that length. As long as it's the same length and same direction, it is considered to be an equal vector. And then I take the second vector and I put it, the tail of the second vector at the head of the first vector. So if that's A and B, vectors A and B, this is vector A, vector B, and so the sum would be a vector from the beginning of the first to the end of the second. So that would be the sum right there, the resultant. Now, if we take the second one, and I'm gonna try to put it, well, my scale stays the same. useful. And it doesn't matter with which one I start. I typically start with the one to the right-hand side, but that's just because of confidence cars. Well, A and B. And then the second vector, again, same direction, same length, it's considered to be an equal vector. And so adding graphically, you're adding it like this. And so the resultant is from where you began to where you ended. And at least the way I've drawn it, hopefully you can see that this is longer than that one. And we can just do some fancy measuring with fingers. Well, that's more than a span. And that's more than a span, so we have to do something better than that. Actually, if I'm doing it that way, middle finger to here. And then middle finger to that same spot puts me to there. So this is a longer resultant. So this is a greater force. And then the last one, similar type reasoning. So the first one, draw like that, and the second one, going back like that. And so the resultant from there to there. Now, if I took the time and care to do it very carefully, it becomes, I think, be a lot clearer that this is the shortest of the three sums. So this would be the smallest total force or net force. A different way of looking at it, in this case right here, part of one force is helping the other force. You basically have two people, if you think about two people pulling on it, two of them are roughly pulling in the same direction. In this case, some of the effort of this force right here is fighting that one. So it's going to weaken the overall force. Similar in some respect to what we did out in the hallway with the rope, where most of the force that was being applied that way was fighting against each other, not fighting against the person in the middle. So here they're helping, here they're hurting, and here they're just sort of don't really care about the other.
So when it's asking for sum of vectors, it's trying to find that value, the resultant, but when it's asking for displacement, that's when you use I hat, J hat.
Well, you could do I hat, J hat with this as well.
But for that, would you need trig?
If they would either have to give you more information, like in the lab that you're going to do where they actually have it on a grid, so you can actually just count how far left or how far up or right, and so on. If I gave you this and gave you the angle, then trig would be involved to get an actual answer. But in this particular case, you're just asked to rank it, and yeah, from greatest to least. And so, as long as you know all the forces are the same and the angles at least appear to be what they are, or are what they appear to be, then you can do a quick and dirty mock-up like that.
So the resultant would be the strongest, or I guess.
So which one did you say was the strongest?
Wait, would that be the third one?
The strongest would be the one with the greatest force, the greatest resultant.
Okay, because it's some of the forces. Okay.
Yeah, so they say net force in the problem itself, which is just the total or the sum. So this would be the greatest, middle, the weakest.
Okay.
You could take it to more of an extreme. Since he doesn't give you angles, then you've got a little bit of play there. If the two forces were in these, practically in the same direction, if you add them together, that's going to give you something almost twice as long. So if that angle gets smaller, the total gets closer and closer to the length of just both of them, the sum of both. If we take an extreme here, where this is practically anti-parallel to this, in other words, the opposite direction, then whatever that is, this is going to cancel out. And that's the kind of thing we did see in the hallway where they were canceling each other out.
And so why will the resultant be larger in that?
Wait, say it again?
Why will the resultant of the sum of the forces be larger than in that triangle if the forces are working against each other?
Oh, that would be the smallest here.
Okay.
Because if you add them together, again, I'm just gonna move this over to here. Head to tail method, where the tail of one is touching the head of the other, then the resultant from where you begin to where you end, is a tiny little force right there. That answered your question?
Probably. Maybe.
Right, I'm gonna come back. I think, Bill, you started out with this one? Was that your question initially? All right, was your question answered?
Yes.
Okay, now back to you. You wanna reword it, or?
I'm still trying to understand why the resultant of, or I guess cause you can move it. So the angle at which they're placed doesn't necessarily matter at first because you can move them.
All right, so the way that he's drawn it in the problem itself is probably closer to what's actually happening, that you've got a rope tied to it and somebody's pulling this way, and here, so there's a rope attached to it and somebody's pulling up. When you wanna find the total force, in other words, what is the sum of the two forces that are there? You're not adding scalars, they're vectors, so you have to take direction into account. So it sounded like you said the angle doesn't really matter. It does matter. Now comes the question of how do you actually get a total? How do you add things that are not in the same direction? And in that case, this is physically what's going on, but the math part is I take one of the vectors, I don't care which one. I take that one, and then the second one, when I'm adding it, is I go to the tip of the first one and do the second, and write the second one. So that would be A and B. So this is just how you add numbers.
Okay.
I guess the analogy would be if you have 2 apples and 3 apples, how many apples do you have? Well, the physical problem is you've got 2 apples here, you've got 3 apples here. The math part, when you actually try to figure out the total, is you just do 2 plus 3. So how you actually do the math parallels what's happening physically, but it's not representing everything.
Okay, I think I understand better. And so when it's asking for the resultant, it's not asking for the total displacement, right? That's 2 different things.
Displacement is something completely different.
Okay.
The math, because I think a number of examples that I do dealt with displacement, but displacement and position and change in position are all vector quantities. The math, this type of thing you would do for any of them.
Okay.
Just the context is different.
Okay.
I hope that's clearer.
Yeah, I'm just trying to understand answer format of what's expected. Because I know when you're asking for displacement questions, like for the example you gave us earlier in another class, the total displacement was 3 meters I hat plus 2 meters j hat.
Right.
But would that work as a resultant? Because that's angular, like there's.
That actually would work as that. However, the trouble with connecting that with this, so let's say that this was, I think you said 200 newtons, or am I just imagining that? 200 newtons. So if we establish this as I hat and j hat, so this would be, just said 200 newtons I hat, 200 newtons j hat. So in the first case, my resultant is 200 newtons I hat plus 200 newtons j hat. That is an actual resultant. Over here though, this can still be 200 newtons I hat, but that one, you got some I and you got some j. No, it's going to the right and it's going up. I'm gonna make up 2 quantities that would add up to 200 if we did it. So let's just say that, for example, B is let's go for a 3, 4, 5 triangle. That's the simplest. $160 newtons I hat plus 120 newtons j hat. That'll work. And so now when you add them together, you would get 360 newtons I hat plus 120 newtons J hat. You add like terms. And over here, in this case, we'll let A be 200 newtons I hat again. And B be, well, it's going that way, so negative 160 newtons I hat plus 120 newtons J hat. And so the sum, well, 200 minus 160, so 40 newtons I hat plus 120 newtons J hat. All right, so now at this point, obviously I made up some numbers, I made an assumption about what the angle was, but hopefully you get the gist of what I'm going for. I have my three sums here in rectangular notation. But when I'm asking about what is the net force, I want to know what is the magnitude. What is the magnitude of this? So mathematically, how would you find the magnitude?
Multiple?
A little bit more complex than that. You would not multiply those two numbers by themselves, definitely.
Well, it's a squared plus b squared.
Otherwise known as, I think somebody just said it, it's very faint.
That's it, the 5,000 zero.
Yep, that's it. So this would be the square root of 40 squared plus 120 squared, which is something. This would be the square root of 360 squared plus 120 squared. And this would be square root of 200 squared plus 200 squared.
And for the Pythagorean theorem to work, it has to be with the right angle triangle, right?
Yes, that definitely has. That is a test if it is a right triangle. If it is a right triangle, the Pythagorean theorem works. And if the Pythagorean theorem works, it is a right triangle.
Thank you.
The hope was on this particular problem is that you didn't have to plug the numbers in. But it'd be nice to think if the numbers were plugged in, you could still at least see an approach. Well, that's what we're going with. It'd be nice if everybody could still do it.
I think I just drew my arrows too short.
Yeah, and that's the downside when you're sketching by hand. Which is why number 5 on the master set, number 2, there's a variety. There is an actual answer because those arrows are a particular length in a particular direction, but there's a lot of leeway about what is correct, or for what you get full credit. Yes, Zoha.
For 45, is this for pulling the tablecloth off of the table?
All right, so doing tablecloth, those are slightly down. Okay.
So I did it in my house and I saw what happened. I saw that the dishes moved more and pulled up and pulled down.
Right.
But I don't know what happened like physically with the forces and everything.
Okay. All right, so I have tablecloth, and something sitting on it. Yeah, I did this demonstration the first year I taught Physics 110. I did this demonstration and forgot to pull down. I pulled up, spilled water everywhere. So if we think about the forces acting on this that's sitting on top of the tablecloth, relating back to the force diagram, this is like box on ground. You know, it's box on cloth on ground. It's object on object on object. So if we look at the forces acting on the box, we have normal force acting up, we have weight acting down. That's pretty much it. And then the tablecloth is going to have, we'll call this Y1. So we got Y1 acting down on the tablecloth and W1. Tablecloth has its own weight and it's also being pushed up on by the table, Y2. And then tablecloth is pushing down on it. Table has its own weight and the floor is pushing up on it. And then I guess we could throw the table in there, or the ground in there. So I've got three weights acting up on the ground. I got the weight of the table, weight of the cloth, and weight of the box.
So the weight of the box when they be on the table too?
No, the weight is always between the small object and the planet.
Okay.
The gravitational force between, I guess there's two things I'm gonna hopefully remember to say. The gravitational force between the box and the table is so insignificant, we're going to ignore it. There's a gravitational force between any two things with mass. So gravitational force between you and the table where you're sitting right now, but you can easily walk away. It's not a particularly significant force. If you're thinking about, if you're at the table, isn't it feeling the weight of the box? Not directly. If the box is in equilibrium, so just think of any object sitting on this table. They're all, for the most part, in equilibrium. Ignoring two other factors that we'll talk about later. Then the normal force, whatever's holding it up, is equal to the weight. That normal force there, so this normal, let's go for the stunning visual effects. Ooh. That normal force there that's keeping the box from falling is the same magnitude as that normal force. This normal force right here is the same magnitude as this normal force. This normal force is holding up two things. It's countering two other forces. It counters the normal force coming from the box and the weight of the tablecloth. So what the table officially feels is that normal force, which happens to be equal to the weight of the tablecloth plus this normal force, and that normal force happens to be equal to that weight. So it's not directly feeling the weight of the box, it actually feels the normal force. However, there are a lot of situations in which those two are equal. Still haven't answered the initial question, but are there other questions at the moment, Bailey?
Why is the second normal force pointing down?
This one?
No, it's the middle one,
That
that
one?
one, why is that pointing down? Cause I thought normal force pointed up.